Hi class, how are you today? Merry Christmas! The learning target for today is to be able to calculate the number of outcomes. 3, you can calculate the number of outcomes. 2, you can calculate the number of outcomes using permutations. 1, you can calculate the number of outcomes using the multiplication rule. And 0, you cannot calculate the number of outcomes. Let's get started. Section 4.3, Trees and Counting Techniques. No, I do not know why that guy is there. So here are some focus points. Organize outcomes in a sample space using tree diagrams. Compute number of ordered arrangements of outcomes using permutations. Compute number of non-ordered groupings of outcomes using combinations. Explain how counting techniques relate to probability in everyday life. When outcomes are equally likely, we compute the probability of an event using the formula P of A equals the number of outcomes favorable to event A over number of outcomes in the sample space. You also know this as relative frequency. The probability formula requires that we be able to determine the number of outcomes in the sample space. When an outcome of an experiment is composed of a series of events, the multiplication rule gives us the total number of outcomes. Consider the series of events E1 through EM, where N1 is the number of possible outcomes for event E1, and 2 is the number of possible outcomes for event E2, and M designates the number of possible events for EM. So what that means is your first event, N1 is the number of possible outcomes for that first event. E2 is your second event. So N2 is the number of outcomes for your second event. So however number of events you have, you just multiply how many outcomes there are for each event. So if you have 3 outcomes in the first event, 5 outcomes in the second event, and 4 outcomes in the third event, and that's all the events you have, you would just do 3 times 5 times 4. That gives you the total number of possible outcomes for the series of events. So 3 times 5 times 4 is 60. You would have 60 possible total outcomes. Jacqueline is in a nursing program and is required to take a course in psychology and one in physiology, anatomy and physiology, A and P, next semester. She also wants to take Spanish too. So she needs all 3 of these classes. If there are 2 sections of psychology, 2 of A and P, and 3 of Spanish 2, how many different class schedules can Jacqueline choose from? Assume that the times of the sections do not conflict. It would be different if there was a conflict, but if there isn't a conflict, we can just use the multiplication rule here. So assume that all of those classes have completely different periods. Creating a class schedule can be considered an experiment with a series of 3 events. There are 2 possible outcomes for the psychology section, 2 for A and P section, and 3 for Spanish 2 section. By the multiplication rule, the total number of class schedules possible is 2 times 2 times 3, which is 12. 2 outcomes for the first event, 2 outcomes for the second event, 3 outcomes for the third event, and then we just multiply those numbers together. A tree diagram gives a visual display of the total number of outcomes of an experiment consisting of a series of events. From a tree diagram, we can determine not only the total number of outcomes, but also the individual outcomes. Using the information from example 9, let's make a tree diagram that shows all the possible course schedules for Jacqueline. So here's a diagram, and we start here, and let's just go in the order we were given them. So first she has to choose which psychology section she wants. And the order in which she chooses doesn't matter. We'll still get the same number of results. So can choose section 1 or section 2 of psychology. Then for A and P, she can choose section 1 and section 2 of A and P. But that's after she's chosen the psychology, so that means we're up to 4 choices. And then for each A and P section, she can choose 3 Spanish 2 sections. So this section right here is choosing psychology section 1, psychology section A and P section 1, and Spanish 2 section 1. If we went to this one right here, it would be psychology section 2, A and P section 2, Spanish section 2. We could go here, psychology section 1, A and P section 2, Spanish 2 section 3. So these here are all the different possibilities. So that means 3 here, 3 here, 3 here, 3 here. We've got 12. 12 possible selections she can make. The tree ends with a total of 12 branches. The number of n branches tells us the number of possible schedules. The outcomes themselves can be listed from the tree by following each of the series branches from start to end. For instance, the top branch from start generates the schedules shown here. So if we just went with the psychology section, here are all the possible abilities. Psychology section 1, so you can choose A and P section 1 and then Spanish section 1, 2, or 3. Or if you chose A and P section 2, you would also have a choice of 1, 2, or 3. So this is half of what the table looked like. It would look identical on this side with all these being 2s for the second part. Alright. Now something you may have seen before in math, factorial. So a factorial is an exclamation point. So any number with an exclamation point at the end is that number factorial. So if I had 3 with an exclamation point, that would be 3 factorial. So if you have 0 factorial, the answer is 1. If you have 1 factorial, the answer is 1. If you have any other number factorial, the way they explain it here is you take that number, multiply by that number minus 1, multiply that by that number minus 2, and keep going until you get to 1. It's pretty much just taking the number you have and multiply by every number less than it until you get to 1. So if I said 5 factorial, it would be 5 times 4 times 3 times 2 times 1. If I said 7 factorial, it would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Each time you're just going down till you get to 1. We've considered the number of ordered arrangements of n objects taken as an entire group. But what if we don't arrange the entire group? Specifically, we considered a dinner party for 8 and found the number of ordered seating arrangements for all 8 people. However, suppose you have an open house and have only 5 chairs. How many ways can 5 of the 8 people seat themselves in the chairs? The formula we use to compute this number is called the permutation formula. As we see in the next example, the permutations rule is really another version of the multiplication rule. The number of ways to arrange in order n distinct objects, taking them r at a time, is n factorial over n minus r factorial, where n and r are whole numbers and n is greater than or equal to r. Another commonly used notation for permutations is NPR. So what that means is n is how many things you have, and r is how many of those things you're using. And you'll see in the example here what we do with that. So let's compute the number of possible ordered seating arrangements for 8 people and 5 chairs. In this case, we are considering a total of n equals 8 different people, and we wish to arrange r equals 5 of these people. So our total number of people is n, 8, and we want to sit 5 of them. So r is 5, because it's of those 8, we want to use 5 of them. Substituting into this formula, we have, so we replace n factorial over n minus r factorial to instead be 8 factorial over 8 minus 5 factorial, which is 8 factorial over 3 factorial. 8 factorial is 40,320, because it's 8 times 7 times 6 times 5 times 3 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then 3 factorial is 3 times 2 times 1, which is 6. Divide that out and you get 6,720. Using the multiplication rule, we get the same results. So instead you just have the 5 chairs, and then you have 8 choices for the first one, 7 choices for the second, 6 for the third, 5 for the fourth, and 4 for the fifth, and then stop there, because you only have 5 chairs. In that same sense, we have 6,720. Notice, essentially what we did is we had 8 factorial divided by 3 factorial. So we would have had 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. So we took those last 3 spots away. The 3, the 2, and the 1 canceled out to leave just 8 times 7 times 6 times 5 times 4. That's a good way to do it if you don't have a calculator. The permutations rule has the advantage of using factorials. Most scientific calculators, and definitely your graphing calculators, have a factorial key as well as a permutations key, denoted the way they are here. In each of our previous counting formulas, we have taken the order of the objects of people into account. However, suppose that in your political science class, you are given a list of 10 books. You are selected 4 to read during the semester. The order in which you read these books is not important. We are interested in the different groupings or combinations of the 4 books from among the 10 on the list. The next formula tells us how to compute the number of different combinations. So this time it's n factorial over r factorial times n minus r factorial. Essentially, the only difference from permutations is this r factorial right here, where, as before, n and r are whole numbers and n is greater than or equal to r. Other commonly used notations for combinations include NCR and NR in parentheses. You'll often hear this as N choose R. In your political science class, you are assigned to read any 4 books from a list of 10 books. How many different groups of 4 are available from the list of 10? In this case, we're interested in combinations rather than permutations. Permutations deal with order, combination are just how many different groups of 10 books taken 4 at a time. Using n equals 10 and r equals 4, 10 is the total number of books, and you want to use 4 of them. We have, so you take the formula, so you'd have 10 factorial over 4 factorial divided by 10 minus 4 factorial. So it'd be 10 factorial over 4 factorial times 6 factorial, which, after you do all the math out, will give you 210. There are 210 different groups of 4 books that can be selected from the list of 10. An alternate solution method is to use the combinations key, often NCR or CNR, on a calculator. How to determine the number of outcomes in an experiment. If the experiment consists of a series of stages with various outcomes, use the multiplication rule or a tree diagram. If the outcomes consist of ordered subgroups of R items taken from a group of N items, use the permutations rule. If the outcomes consist of non-ordered subgroups of R items taken from a group of N items, use the combinations rule. Now time for the sponge. When picking out clothes to wear, a person can choose from 3 shirts, 5 pairs of pants, and 2 pairs of shoes. How many different outfits can be chosen? Number 2, how many ways can an interview committee choose an Algebra 1 teacher, a Geometry teacher, and an Algebra 2 teacher if 12 applied to become a math teacher? This is, of course, assuming that all these teachers can teach all of these subjects, though that's usually the case. And number 3, how many ways can a synchronized swim team choose 6 performers from its 15 members? Alright, that's it for the lesson. Once again, please make sure to take notes in the entire lesson, and hopefully you listen to it, because I said some important things there today. Take a picture, video of all of it, submit it all to Google Classroom, and have a good night.